Hi. Now we will see the meshing. We are already done with our problem statement and our geometry. So here you can see the green sign. So our geometry is done and we can proceed for our meshing. So double click your meshing and your mesh module will start. So here is our geometry. So we can mesh this whole geometry with different approach. We can map it, or we can take each and every edge and size it. So it depends on how complex your problem is and what kind of things you want to resolve from your simulation. So in our case, we will go for a very simple meshing that everybody can try or everybody can do. So we will go with the ANSYS default mesh. So for that, select the mesh and generate the mesh, and it will generate with its default setting. So as you can see here, this mesh is a very simplified, very coarse types of mesh. So it will not work in our case. So we have to refine this mesh. First of all, we will refine it by the default setting. So go to sizing and here relevance center, change it from coarse to fine. Then update, it will update, and as you can see here, the mesh is a little bit finer, but still the mesh is too coarse for the simulation. So what we can do, we can play with these numbers and we will get a reasonable size. So right now the maximum size is almost 2.8 centimeter and the maximum face size is 1.4 centimeter and the minimum is 0.1 millimeter. So we will reduce this maximum size to 1 millimeter and we will try to see how the mesh will look like. So change it to 001, and here you can see this yellow sign. That means your maximum size is smaller than your maximum face size. So you need to change the maximum face size. Also, you can make it smaller or you can keep it the same. So your maximum face size and your maximum size should be same, or your maximum size can be smaller than your maximum face size. So now the yellow sign is gone. So then we will update our mesh and we will try to see what happened. So here is our mesh. As you can see here, this is really a very fine mesh, and here you have a mixed mesh. In the mixing section you have a very mapped structured mesh, but here when you have a curvature you have some unstructured mesh. So you can change it, you can play with the numbers, and you can fix your mesh size. Right now if you want to check how much you have, here you have almost 48,000 nodes and 46,000 elements. So it's quite reasonable, but if you want to resolve a very detailed, you can reduce the mesh size much smaller. So we will stick with this number, and one more thing we need to do right now, that is we need to define the boundaries. So select, as it's a 2D drawing, and 2D surface, we will select the boundaries with the H selection tool. So select the H selection and select this. So this is our hot water inlet. So we will write hot inlet or inlet 1, whatever you want. And this edge is called inlet, and this edge is our outlet. And other boundaries are wall. You can specify these walls as mixing wall. You can specify these walls as hot water tube wall, whatever you want. But actually we don't need to define those walls because we don't have anything to calculate on those walls. So we will stick with a regular wall and update one more time. Now if you check here in the workbench, you can see the green sign. So your mesh has been done, and we can proceed to setup. So we will go to setup and we will set up our case, and we will see how the mixing works. So now we will set up our case for the mixing problem. So as you can see here, our geometry and meshing is done, and we can proceed to the next stage, that is the case setup. So go to case setup and your Fluent will start. So start your Fluent, and once your Fluent is start, always check your case, check the minimum volume, and check the quality of your mesh. So right now our orthogonal quality, minimum orthogonal quality is 0.81, which is not bad. So we can proceed with this mesh easily. So here, like the previous problem, we will go through all of these steps. So for mixing problem, our working fluid is water, and we have different temperature. So in general, we will use pressure based solver with absolute velocity formulation because we don't have any moving parts, and we will use transient flow problem. As it's water, we can also use gravity. So from meshing, you know that our coordinate system, this is your y-axis and this is your x-axis. So our gravity is working downwards. So put the value of your g minus 9.81 meter per second square. And this is a 2D planar problem. So we are done with the general option. You can change the unit in the length. You can change the unit from meter to inch, and then go to model. Here our working fluid is water, so we don't have any multi-phase flow right now. In mixing, we can also use multi-phase flow for different liquids. For example, if you have two different liquid going through one tube and another tube, let's say one tube is containing water, another tube is containing methanol, and you want to see the mixing process of water and methanol, then you can model with multi-phase flow. But here we have only single phase, so we don't need to turn on the multi-phase. We have different temperature, so we need to turn on the energy equation. So turn on the energy equation. For viscous model, we will use standard K epsilon model, a very standard simple turbulent model. We don't have any radiation. we don't have any heat exchanger problem, we don't have any reaction in this particular problem. So all of these options will be turned off, only the energy and the viscous model will be used. Now go to material. Our working fluid is water, so we have to specify the material property of water. So go to create option, and here you have the fluent database. Go to database and find out your liquid water. Here is your liquid water. Check all of these parameters. If you want to change these parameters, you can change here. If you want to define new parameters, you can also define new parameters. So select copy and then close it. So now you have two fluid, one is water and another is air. We don't need this air, so we can delete this air. So select this air and try to delete this. Now as you can see here, you can't delete this material right now. There is something going on. The thing is, if you go to cell zone condition, you have a single zone, that is this surface, and the surface type is fluid. And if you go to edit option, the material is right now air. So this surface is defined as air, that's why you can't delete the air. So if you change this air to liquid water and select OK, now go back to material and select this air and try to delete it. Now it will delete. So always make sure that what types of material are in your surface or in your body. It's very important. Now we have liquid water. Now we can specify our boundary condition, which is very important. So in the boundary condition, we will consider 0.1 liter water is entering through the hot tube and the same amount of water is entering through the cold tube. So go to hot inlet. This is velocity inlet, so change it to mass flow inlet. Okay, now you have the mass flow inlet, so you need to specify the mass flow. So we are considering 0.1 liter per second. So 1 liter water is almost 1 kilogram of water, and 0.1 means 0.1 kilogram, that is 100 gram. So 0.1 kilogram water, and the direction is normal to the boundary. So this is mass flow. The amount of mass flow is this, and our subsonic or supersonic initial gauge pressure is 0, and the direction of the flow is normal to this boundary. And here in the turbulence section, as this is an internal flow, so we will specify our intensity and hydraulic diameter. So we will consider intensity as 10% and our hydraulic diameter in inch is 1. In the thermal section, as this is a cold inlet, we have room temperature, that is 300, so this is fine. We don't have any multi-phase flow, we don't have any radiation, no reaction, so we don't have anything else to provide, so select OK. Similarly, for hot inlet, change the type, change it to mass flow inlet, and then you have the similar amount, 0.1 kilogram per second, and change the direction normal to the boundary. Change the turbulence option, intensity and hydraulic diameter, 10% intensity and 1 inch hydraulic diameter. And thermal, we have 363, that is 90 degrees Celsius. Select OK. For outlet, we will use outflow. So select outflow and flow weighting is 1, and wall surface is thermal boundary condition, you have temperature 300, so that's okay. Now we are done with our boundary condition. So go to dynamic mesh. We don't have any dynamic mesh right now because we don't have any moving part in our domain. Our reference value, you can check the reference value from anywhere. Let's say hot inlet, so you can check these values according to our hot inlet. Now solution method, we will use simple scheme with least square cell based discretization for gradients. For pressure we will use standard discretization. The momentum is right now second order upwind, we will keep that. For turbulent kinetic energy or for K, we will use also second order, and for epsilon, that is turbulent dissipation rate, we will use second order upwind. You have also the energy, which is also selected second order upwind. This second order upwind discretization method will give you more precise result compared to the first order upwind method. And now solution control, you can check the relaxation factor. As I told earlier that if you don't know, don't change these relaxation factors. If you really know what you are trying to do and what would be the behavior of your solution, then you can change these relaxation factors. Otherwise you don't need to. So keep it as it is. Now go to monitor. Here in the residue you can see the convergence criteria, and you can also see the print and plot option. So select OK. Now solution initialization, we will use hybrid initialization. So select hybrid initialization and initialize, and it will start initializing. Now go to calculation. As you can see, in general option we have transient problem, so it's time dependent. So in calculation you can see the change. If you go here and select steady and go to run calculation, you can see you are asked only to provide the number of iteration. But when you select transient and if you go to run calculation, you are asked two different parameters. One is the time step size and the number of time step, and here the maximum iteration for each time step. So you need to understand these parameters. First of all, the time step size, that means when you have a transient problem, you need to provide the time step, which is delta t in mathematical term. So when we discretize our governing equation, we have a delta t value, that's our time step. So it depends on your problem setup. So when you have a very high turbulent flow, your time step should be much lower, but when you have a low turbulent flow or laminar flow, your time step will be much higher. So it totally depends on your problem and your problem setup. We can also calculate this time step based on Kolmogorov scale. So you can check this online, or you can check this any fluid mechanics book how to calculate the Kolmogorov scale. Then you will have an idea about the time step. So right now we will stick with a 0.1 second time step. So for each iteration, so now this 0.1 second means for each iteration the solution will proceed for 0.1 second. and this number of time step, if you put 10, then this will indicate the actual physical time for your simulation. For example, if your number of time step size is 0.1 and your number of time step is 10, then if you multiply those two things, then you will get 1. That means for physical actual 1 second of time. So that means if you have a very smaller time step, you can resolve the solution at a very slow speed. That's the thing. So when you have a very high turbulent flow, you have to capture all of the turbulent property. So you need to proceed your solution very slowly. So you need to put your time step at a very small number. But when you have a low turbulent flow, then you can increase your time step. Now if we put 100, and then you can see if we multiply this time step with the number of time steps, then we will get 10. That means for actual physical time, if after 10 seconds we will see the simulation results. So this is the significance of time step and number of time steps. And here you have the maximum iteration for each time step. So right now it's 20. So for each time step, it will iterate 20 times and it will give you the results. So right now we are not interested to those detailed calculation. So we will stick with one iteration for one time step. And then we will calculate. So start calculate. And as you can see, it's calculating. And the behavior of your continuity, your velocity, and the temperature is decreasing. So it's a good sign that your solution is converging. So as you can see here, we finished our simulation. Here you can see the flow time 10 seconds. So this 10 seconds is your actual physical time that the flow is flowing for 10 seconds. And for this 10 seconds we iterate 100 times. So if you put here 10, for each time step it will iterate 10 times. So for 100 time step it will iterate around 1000 times. So you can see the difference between these things and how it works. So in the next tutorial we will try to see the results and we will try to see some post-processing. Thank you.